Hey folks, here I am in the yurt. I'm doing some math. I'm going to walk through operations with complex numbers. We're going to be doing all the operations except division. So we'll be doing adding, subtracting, and multiplication between two complex numbers, both analytically and graphically. We're going to be working through the same thing we did in class, which was on page S15 in the Engage New York work, which is available on Blackboard. So you can download that and go along with this, or it's already in your notes. So here we have the complex plane, and we have two complex numbers, a and b. We have the real number line, and we have the imaginary number line. We're going to go ahead and plot both of these. So let's plot a. Let's make a green. So we're going to go over 1 and up 3 because it has a real component of 1 and an imaginary component of 3. So that 3i gets plotted up here. And then we have b. Let's switch colors here. Is 2 minus I. So our real component is 2. And then this minus I is the same as if the coefficient were -1. So we'll plot it right down here. And that is B. And so now let's go ahead and if we were to consider them as analytical numbers that we can work with by adding and subtracting using the values, we would stick with these values over here. If we want to work with them graphically, it's very helpful to consider them as vectors. And a vector has a magnitude or a length and a direction. So this length of this line that connects the origin to the point that we plotted for A is the vector that represents the complex number A. And then we can do the same thing for B. Let's go ahead and plot that one right here. And there's B. Now let's work on what A plus B is. So let's jump frames where I already have those things done. We're going to work on how to add them both analytically and graphically. So analytically, we add the real part to the real part. We add the imaginary part to the imaginary part. So 1 plus 2, really hard. And then 3 plus -1 is -2. No, it's not. It's +2. And it is our imaginary part. So we end up with 3 plus 2i. And if we were to come over here and plot a plus b, that would be over here, 1, 2, 3, and up 1, 2. So we get this point right here of a plus b. So we can see how we can come up with it analytically by treating the real numbers and the imaginary numbers separately and adding them respectively. We can also get there graphically. So remember that we can consider this as a vector. The vector b goes over 2 and down 1. That's its direction and its length. Its location is not part of it being a vector. So we can move it around anywhere and still use it as the complex vector that represents this value b. So to add b to a, we would start where we ended with a and go over 2, so 1, 2, and down 1. And look, we arrive at the same place. Let's go ahead and sketch that. So that would be right here. We end up with the vector b connecting a and then b ends up being a plus b. Now we know that a plus b is also equal to b plus a. So let's go ahead and do that one. So if we were to add a to b instead of b to a, it would look like this. And sure enough, we have something that looks like a parallelogram. It's a little wonky down here, so I must have been off by just a little bit in the way that I plotted the points. But we should get a parallelogram where the values, the lengths of a and b are the same, and both of them bring us to this point here, a plus b. We can then also work through subtraction the same way. So a minus b analytically looks like a, the real part, minus b, the real part, which would be 1 minus 2, which would give us -1, and 3i minus -i. So 3 minus -i would be minus a negative is plus. So we have 3 plus 4. 3 plus 1 is 4. We end up with -1 plus 4i. Plotting that over here, we come over real part, -1, imaginary part, 4. So that's up here. And that is the point a minus b. And we have extended a and then subtracted b, which is the same as adding -b. So if B runs from the origin over to the point B as a vector, then its opposite will be rotated 180 degrees. It would be like going from the point B back towards the origin, or from the origin exactly 180 degrees this way. So negative B is this piece right here going from where we ended with A out to B right here. So this right here is negative B. And what we've done is we've just added vectors where we have our path from 0 to A, that first part. And then we're adding negative B to get from 0 to A minus B. And the total path right here is our final vector. That's the thing we left out earlier. That if we wanted to represent A minus B as a vector, that would be this vector right here. And that vector has components of -1 plus 4i. And similarly, this A plus B has components of 3 plus 2i. You see both of those there. Then we can work on something even more interesting, which what if we were to scale one of these? Let's scale A. So we're going to double every value on A. This is like distributing that 2 across the 1 plus the 3i, because A is equal to 1 plus 3i, so I've just replaced A with what it's equal to using parentheses, and that's going to give me distribution 2 plus 6i. It really is that straightforward. And then I can plot that by going over 1, 2, and up to 6 here. And that point right there is the point that represents 2a, or 2 plus 6i. And you might notice that it's what we would get if we did the vector a, graphically finding it, and then added a again, because a plus a should be 2a. Let's go ahead and draw out that second vector a from where we left off with the first one. Yeah. So this is a again. So we have a plus a for the vector a, and the vector a would get us to 2a up here. And then lastly, what we have is multiplication. We'll do multiplication analytically. So a times b is going to be, I need a little more space for this one. I've seen some people doing a box diagram. I am a fan of parentheses, 1 plus 3i. But whatever works for you is what you should be doing, 2 minus I. And so I've got everything in this set of parentheses has to multiply everything in this set of parentheses. So I'm going to have the 1 times the 2 and the 1 times the negative I, and then the 3i times the 2 and the 3i times the negative I. So let's do that. So 1 times 2 is 2. This is still what it equals. 1 times negative I is minus I. 3i times 2 is going to be 6i. And then 3i times negative I is minus 3i squared. So now let's see, what can we do? I've got that 2 is just going to be rewritten. I've got negative I plus 6i gives me plus 5i. Okay. And then minus 3i squared. Well, I know that this I squared is equal to negative 1. So that's minus 3 times negative 1. So I have 2 minus negative 3, so that gives me 5. So I have 5 plus 5i, which we can come over here and plot. That was this value that we just found right here. So a times b is what that is. Let's put that one on the diagram. So here we go, over 5 and up. 5, ooh, can I find it? I found it, right there. So this is a times b. There's a lot of stuff going on here. Let's go back to our first slide. Here we go. So there's a and there's b, and we just found that a times b equals 5 plus 5i. So we're going to go over 5 and up 5 and plot it. This one is interesting. The way that we get to this is that we have rotated. So if we imagine first having the real number line here, the length of 1, if we were to multiply 1 by 2 minus I, we have extended it to the length of b and rotated out this way to the right. So we could imagine then starting with a being this length, we're going to extend a the same amount that we extended our just a unit vector that's only one long and doesn't go off of the real number line. We're going to extend it this much further. So that is actually the square root of 5 longer than 1. So we get that from 2 squared plus 1 squared. Square root is the square root of 5 for this length. That one is that much longer, a little bit more than twice as long, and rotated this much. We're going to rotate this about the same amount. And we end up having a vector that is rotated the same amount from where A was as the real number line is rotated to B. Let's undo and undo. And we can also imagine this being, if we start with B and then rotate from B the same amount that we rotate from the positive real axis to get to A, that's how much we're rotating to get over here to our product of A times B. You can see that this angle in here is about the same as this angle between the real number line and A. So we're rotating when we multiply. And also we're scaling from 1 gets to be, what's that? 3 squared plus 1 squared. Let's come over here and do that. So this length is the square root of 3 squared plus 1 squared is square root of 10. So this length right here is the square root of 10, a little more than 3 times as long. So whatever length this is, when we multiply it by A, it's going to be 3 times as long, because that's how much longer A is than 1, and rotated however much A has been rotated from the real axis. So that's a graphical representation. We're going to come back to that graphical representation. It's not the way we're going to be doing multiplication for the end of this unit. We'll be doing multiplication the analytical way, which is actually not there, but it's on this page. We'll be doing multiplication the analytical way, where we go through this process here. But I want you to see the vector process for addition and subtraction and scaling. Those are really straightforward. And we'll come back to this at the end of the year after we've done a lot more with angles and trig functions. And we'll be into rotating things on the complex plane and why the complex number system is so useful. People that have to do things like rotating them, for example, animators would do that. That's it. Thanks, everybody. And I hope this helped. If you have any questions, please do feel free to reach out to me, and I'd be happy to connect with you if you need it. Bye.